All right, well, let's continue on. We'll make the push to lunch. And now what I want to do is I want to spend a little time talking about the nervous control of breathing. So using how the nervous system works. All right, so where does most of the nervous control of breathing occur? Yeah, so it occurs in the lower brain. And does that surprise anybody? It shouldn't, because what is the lower brain responsible for? It's responsible for life essential tasks. Okay, so your cardiac centers, and as you guessed, your respiratory centers are located. They're located in the pons and the medulla of the brain primarily. And so the way that this works is you have different receptors in your body. And you have three general categories of receptors, or two general categories. You have what are called chemoreceptors. And what do you think what does chemo mean? It means chemical. So these are receptors that monitor the chemical environment of the blood plasma. Specifically, when talking about breathing, the chemoreceptors monitor the pH. And what is pH a measure of? It's a measure of acid, right? Right, so we're looking at acid levels. Okay? And so chemoreceptors measure acid levels. And then you have what are called mechanoreceptors. And what is that? Stretching. All right. Now, just as the case in cardiology, we have stretch receptors in our blood vessels, like our carotid arteries and the aortic arch, and in the kidneys that measure blood pressure and cause physiological changes in response to blood pressure. We also have mechanoreceptors in the lungs, in the lung parenchyma. And as you might guess, when these receptors get activated, they send information, into the brain saying, hey, we're getting stretched out here. Maybe you want to inhibit that inhalation, right? You guys cool with that? Now, likewise, you have two general areas where chemoreceptors exist. We have what are called central chemoreceptors. And these are chemoreceptors that monitor the pH of the cerebral spinal fluid. And then they send that information to the brain, to the pons, the medulla. And then we have what are called peripheral chemoreceptors. These are chemoreceptors outside of the brain that monitor the pH of blood plasma in our blood vessels. And we tend to find these in very large vessels, such as your aortic arch. Okay? And that information gets sent into the brain. Are you guys cool with that? That sort of makes sense? Okay, so if we enlarge this part of the brainstem here, and that's what I've done over here, is I've enlarged that. So we've got the pons here, and we've got the medulla down here. And then, of course, the spinal cord would be here. We have two centers within the pons, and these two centers make up what we call the pontine respiratory group, or the pontine respiratory group. All right? And these two centers are the pneumotaxic and the apneustic centers. This is really convoluted, kind of how this works, so I'm going to try to make it as simple as possible for you guys, because it is a little convoluted, okay? So, the apneustic center is pretty much always on. The apneustic center pretty much always says inhale, 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 and it is just always saying inhale, 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 inhale. You guys okay with that? Always. And if the pH of your plasma becomes more acidic, Okay, that information is going to get integrated into that apneustic center and other areas, and that's going to make it go inhale more, right? It may activate it more. So you always have this center that is constantly saying to inhale, inhale, inhale. So what do you suppose you need in addition to that? You need a center that says stop, exhale, 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 right? And that is the pneumotaxic center. The pneumotaxic center is the primary antagonistic center, okay? And the apneustic center is the primary inhale center, okay? And the pneumotaxic center can actually send inhibitory information down into the apneustic center, okay? You guys good with that? Now the information in the pneumotaxic and the apneustic, the information from the pontine respiratory group, before it leaves the brain, it is further processed, or I kind of look at it as fine-tuning, quote unquote. And that fine-tuning occurs further down into the medulla. And there are two centers within the medulla. There is what's called the ventral respiratory group, or the VRG. And so what part of the medulla is that going to be located in? Toward the front, the ventral aspect. And then you have the dorsal respiratory group, or the DRG, and where do you suppose that's located? The dorsal, toward the back, okay? So information from the pontine respiratory group, the pneumotaxic and the apneustic centers, goes down into the ventral and dorsal respiratory groups, okay? And the dorsal respiratory group is primarily stimulated by the apneustic. Okay, so the apneustic sends positive stimulatory information into the dorsal, and then that causes the dorsal to activate and send information down the spinal cord and into the lungs, and causes, or not into the lungs, but into the muscles of the lungs, the diaphragm, and then what we call the accessory muscles, the external intercostals, the internal intercostals, the sternocleidomastoid muscles, all of those accessory muscles, and cause us to inhale. Does that make sense? Causes those muscles to contract. You guys cool with that? All right. Now, the ventral respiratory group is a group that contains both inspiratory and expiratory neurons for inhalation and exhalation. And this appears to be a very important regulator during physical activity, okay? Where there is a increased demand on the respiratory system, and you may need to take deeper, faster kinds of breaths, okay? Does that sort of make sense? Okay. So you get your two main centers up in the pons, the pneumotaxic and the apneustic. The apneustic is your primary inhale, and your pneumotaxic is your primary exhale, to stop inhalation, right? And then there is some fine-tuning of that information that occurs down in the medulla, and then once that occurs, that information goes out, okay, through the spinal cord. And what is the primary nerve of breathing? The phrenic nerve. And the phrenic nerve innervates which muscle? The diaphragm. How many major branches of the phrenic nerve do you have? Two. You've got the right and the left. Good. And so you have the right phrenic goes to the right diaphragm, the left phrenic goes to the left diaphragm. Does that kind of make sense? And where does the phrenic nerve, what general area of the spine does it come out of? Yeah. And as the saying goes, C3 through 5 keeps the diaphragm alive, right? And so we know that high spinal injuries above the level of C5 may compromise the phrenic nerve and may compromise your patient's ability to breathe. Okay? You guys okay with that? Does that kind of make sense? So, what is the primary stimulus to breathe? our primary drive to breathe, okay? The primary drive to breathe, okay? This is very important moving forward. Your primary stimulus is pH, okay? Acid levels. pH is the primary drive to breathe, okay? The so-called hypoxic drive is secondary, okay? You have to be really hypoxic before that drive becomes relevant, becomes a relevant player. You guys okay with that? Okay, so it is the pH, mainly of the cerebral spinal fluid, which becomes your primary stimulus to breathe. You guys okay with that? Does that kind of make sense? Okay. And let me give you some examples that help demonstrate this. So, there is a kind of diving that occurs called free diving, where people hold their breath and they dive for as long as they can. What's that?
That's crazy.
Yes, that is crazy. What do these divers sometimes do in order to help them stay underwater longer? They hyperventilate. How does hyperventilation help us stay underwater longer? Say it again. So does hyperventilation increase our oxygen levels? No, right? If you once your hemoglobin's oxygenated, unless you're talking about like 100% oxygen and you're flushing out nitrogen, right? You're replacing nitrogen a lot. But just room air, hyperventilation, you're not doing much, right? What you're really doing is you are blowing off carbon dioxide. You are making your pH alkalotic, right? And when you become alkalotic, the primary mechanism for breathing is like, oh, acid levels are very low. I'm cool. When we go into lab today, what I want you guys to do is I want you to put yourselves on the cardiac monitor. And then I want you to hold your breath for as long as you can, okay? And I want you to watch and what we'll do is, you've got your nasal cannula, right? Oh, perfect. Let's torture Coulter today, right? So what we're going to do is we're going to put Coulter on the cardiac monitor, okay? We're going to hook him up to in-tidal CO2 monitoring, right? And then what we're going to do is we're going to have Coulter hold his breath for as long as he can, all right? And we're going to watch his saturation. What do you suppose is going to happen to his pulse his O2 saturation? Not going to do a whole heck of a lot, right? What's going to happen to Coulter, though? It's going to get more and more anxious. It's going to get that air hunger until what? Right? And the whole time, his saturation will likely be above 90%. But when he starts breathing again, what might we see with his carbon dioxide? It'll be elevated initially, and then as he starts to breathe, it'll go back to normal, right? And so that's a really good experiment that we can do, right, to test this whole hypothesis. But does that make sense? And that should also make sense in patients like DKA. You guys are familiar with diabetic ketoacidosis? What is the general respiratory pattern for someone in DKA? They have that Kussmaul's pattern, right? That fast, deep. Now, are they breathing fast and deep because their oxygen levels are low? No, it's because they're acidotic. their acid levels are high, and that high acid level is stimulating their respiratory centers. Does that make sense? You guys okay with that? Cool. All right. Very, very good. All right. How are we doing on time? Okay. Well, let's get ahead here. All right. So we'll cover this real quick, and then I'll get you guys on a break. How does that sound for lunch? Okay. So let's talk about gas transport now. And I'm going to start at oxygen, and then I'm going to work my way to CO2. We will not get to carbon dioxide transport. So here's an oxygen molecule. What do we know about oxygen? It's small, and is it polar? What happens when you covalently bond two exact same atoms together? Does that result in a polar or a non-polar covalent bond? Say it again? Non-polar, right? Because two oxygen atoms have exactly the same electronegativity, right? And it is difference in electronegativity that makes things polar, right? So oxygen is much more electronegative than hydrogen. So that makes water polar. But if you have two oxygens, then the electron density is shared equally throughout that molecule, right? So this is a small non-polar molecule. Well, what do we know about our blood plasma? What's the deal with the blood plasma? What's going on there? Is it polar or non-polar? Yeah, blood plasma. Is it polar or non-polar? It's polar because it's made primarily of water, right? Well, what do we know about non-polar molecules and polar molecules? Do they mix very well? No. You cannot dissolve a non-polar molecule in a polar solvent. So non-polar molecules like oxygen and carbon dioxide are not easily dissolved in water, which means we can't dissolve oxygen in our blood very easily, right? Because our blood is polar and the oxygen's non-polar. So we need some other mechanism for getting oxygen transported around the body. Does that make sense? And that mechanism is primarily what? A protein. We can attach the oxygen to a protein, and then that protein can transport the oxygen to where it needs to go. Does that kind of make sense? And the primary protein is what we call hemoglobin, right? Hemoglobin is a quaternary structure protein that consists of 4 chains or 4 globulins, okay? So you have what are called alpha chains and beta chains. You have 2 alphas and 2 betas, and the difference between them is not relevant for what we'll be talking about as paramedics. And at the center of each of these chains, there is an atom of what? Iron. There is an iron atom. And if you look down here, that iron atom, that's Fe, Fe is the chemical symbol for iron, is surrounded by what's something known as a porphyrin ring, okay? And basically what you have is you have nitrogen atoms, and nitrogen atoms have electrons, kind of a pair of electrons on them like that. And you have nitrogen atoms on 4 sides coming in and surrounding this iron. So I'll draw them like that, okay? And electrons, are they positive or negative charge? They're negative charge, so are they attracted to positive or negative? They're attracted to positive, and it just so happens the iron in the hemoglobin exists in a very special, what we call oxidation state. And the oxidation state for iron in hemoglobin is what we call its ferrous state, or it is a +2 ion, which means that it is missing 2 electrons, so it has a +2 charge, which means that electrons are going to be attracted to it. Does that make sense? So what happens is you have this Fe+2, this ferrous iron, and those nitrogen atoms are kind of attracted to it, the electrons, okay? And then down here at the bottom, the iron is attached to the globulin by an amino acid residue. So you have all four sides of the iron and the bottom of the iron. Is the iron completely surrounded? Or is there still one opening? There's one opening here at the top where something could come in. Does that make sense? And once you get 6 things that surround the iron, then it's completely surrounded, right? And if you look at the structure of oxygen, each oxygen atom in the molecule has a pair of electrons on it there, right? You see that? You've got 2 pair, a pair up top, a pair on the bottom, and then you have your pairs in the middle where you have your covalent bonds. And those electrons are going to be attracted to this opening where you have the positively charged iron, right? And so the oxygen's going to come in and it's just going to kind of pop on top there where that attraction occurs. And that's how it works, more or less. Does that make sense? Okay. All right. And so one molecule of hemoglobin can transport how many molecules of oxygen? 4 molecules of oxygen. You guys cool with that? Now, let's go in a little deeper. Have you guys ever wondered, well, okay, I understand that hemoglobin wants to attach to oxygen, right? Or oxygen will attach to hemoglobin. I understand that, but the oxygen somehow has to detach, right? Does that make sense? So far, we understand that oxygen can attach, but what makes oxygen detach? Well, proteins, as we talked about in pathophysiology, proteins have a specialized shape, right? Known as a conformation. You guys familiar with that term? And conformation, okay, also means that a protein has a special function. And when you change the shape of a protein, you change the conformation, you change how that protein acts. So what if I were to change the conformation of hemoglobin and make it less likely to hold on to oxygen? Well, then it would release the oxygen, wouldn't it? And wouldn't it be nice if there was some mechanism that would make the hemoglobin want to hold on to oxygen in the lungs and then release oxygen in the tissues that need it? Some sort of mechanism or mechanisms that would change the conformation of the hemoglobin. What do you think? And in fact, there is such a mechanism. One of the things that changes how hemoglobin works is pH, acid levels. And we haven't talked about this yet, but we will, not today. We won't have enough time to get to this. But what happens to carbon dioxide in the body? It is turned into an acid, actually. Carbon dioxide is transformed into an acid so it can get dissolved in our blood. Okay? So wherever I have lots of CO2 being produced, what happens to the pH? The pH decreases, right? And the acid level increases. So if I have tissues here, and these tissues need oxygen, right? They're working, they're making a lot of CO2. And so this is a blood vessel here. What is the pH in this area of the blood vessel? The pH is going to be low and the acid level is going to be high. And so what happens is as that hemoglobin, those little oxygen molecules on the hemoglobin, passes through that area where the pH is low, that pH will induce a conformational change. Okay? It will change the function of the hemoglobin and make the hemoglobin have a lower affinity for oxygen, and it will release its oxygen. And then as the hemoglobin that is deoxygenated now, right? So the hemoglobin gave its oxygen up. As it goes through the lungs where the pH is higher, that will induce another conformational change that will make hemoglobin want to hold on to oxygen. And then it gets loaded up with oxygen, and then once the hemoglobin goes back through the tissues where the pH is lower and the acid is higher, release and rinse and repeat. Does that kind of make sense? That, where the hemoglobin releases oxygen in response to low pH, is known as the Bohr effect. B-O-H-R, the Bohr effect. The Bohr effect is where hemoglobin releases oxygen in a low pH environment. Does that make sense? And then the Haldane effect is more or less the opposite of that, where you have onloading of oxygen occurring in the lungs where the pH is higher. Does that make sense? And that's one of the mechanisms that acts upon hemoglobin. Now, you guys have taken chemistry, may be familiar with the term Bohr, right? And you may have heard the term the Bohr model of the atom. Guess what? It's not that Bohr. Yeah, it's actually the dad. Yeah, Daddy Bohr was a renowned physiologist who came up with this. And then one of the sons, Niels Bohr, was the renowned physicist who came up with the Bohr model of the atom. I bet that family had some very interesting dinner conversations, huh? Yeah. Are you guys okay with that? So far, so good? Okay, so that's... Okay, we got some time. That gives rise to another way of looking at hemoglobin. And that way is known as the oxyhemoglobin dissociation curve. That's this monster up here. And all we do is we plot the oxygen saturation and the partial pressure. Okay, you guys okay with that? And as you might imagine, at higher partial pressures, I'm going to have a higher saturation of oxygen, the hemoglobin, right? Okay. But, and that's this normal curve here, right? So down here, okay, I have no oxygen on my hemoglobin, right? And then what happens? That curve goes up, and then it flattens off. Why do you suppose the curve flattens off up here? Why doesn't the curve continue to go up? Why doesn't the saturation continue to go up as the pressure goes up? Because you've basically saturated all the hemoglobin that's going to be saturated, right? So it curves off. And this is known as a sigmoid curve. A sigmoid curve kind of makes an S. So why do you think the curve is so steep in here? What's going on there? Sort of. Sort of. What happens here is the more oxygen that gets attached to hemoglobin, the more hemoglobin wants to get a hold of more oxygen. So when hemoglobin has no oxygen attached, it doesn't have a very high affinity. And then once the first oxygen gets attached, it has a higher affinity. And then the second, even higher. The third, even higher yet. And so what happens is once that first oxygen's attached, the hemoglobin has a higher affinity, higher, until it gets fully saturated. Does that kind of make sense? But we can alter how that hemoglobin works. We can shift. We can shift the affinity that hemoglobin has for oxygen. Okay? And so we can do what's called a right shift. Let's talk about that first. A right shift is hemoglobin that has a decreased affinity. And what have you noticed here? Is my saturation higher or lower in this red, this right shifted? Because if this is our baseline, this would be to the right and this would be to the left, right? It is lower, right? Do you guys see that? So at this partial pressure here, the saturation is lower in the right shifted curve than it would be in the in the normal curve. Do you guys see that there? So that means that this hemoglobin in the right shifted scenario doesn't want to hold on to oxygen as much. Does that make sense? So a right shift, think of releasing oxygen. A right shift, the hemoglobin releases oxygen. It has a decreased affinity. You guys okay with that? There are three major things that I want you guys to know about right shifted. Raised acids, right? Because that's the Bohr effect that we just talked about. Raised body temperature. If you get a fever, okay, your hemoglobin will be right shifted. And raised 2,3-diphosphoglycerate, or 2,3-DPG. And I want you to think of 2,3-DPG as being a crowbar. It is like a little crowbar that can pop oxygens off of the hemoglobin. And that is important in certain disorders, COPD being one such example. Are you guys cool with that? Right shifted hemoglobin releases its oxygen, decreased affinity, think of your R's, raised acids, so that's a low pH, raised temperature, raised 2,3-DPG. You guys cool with that? Now, a left shifted situation, however, I think of lock. The hemoglobin locks onto the oxygen and won't let it go. You guys cool with that? And so the hemoglobin has an increased affinity. Make sense? I think of my L's. Low acids, low temperature, low 2,3-DPG, and lots of carbon monoxide. Carbon monoxide causes a severe left shift of your hemoglobin. Okay, so somebody who's very alkalotic is going to have very left shifted hemoglobin, right? The affinity will be very high. It wants to lock onto that oxygen. Does that make sense? Is that a problem? What's the problem there? It's not going to deliver it to the tissues, right? So if you have some patient that maybe they're really sick or they've had a trauma and you hyperventilate the heck out of them and you make them alkalotic, you left shift their hemoglobin, that's hemoglobin that is not going to want to deliver that oxygen to those tissues that need it very easily. So yet another problem associated with hyperventilation. Does that make sense? Okay, that's the oxyhemoglobin dissociation curve. Okay, just a couple more things and we'll get you out of here. There are abnormal oxidation states of hemoglobin. The most common is where iron loses an extra electron. So instead of +2 in its ferrous state, it's a +3, or what we call ferric state. Iron in its ferric state in hemoglobin cannot transport oxygen. And that's what we call methemoglobin. Okay? So if somebody has methemoglobinemia, the iron in their hemoglobin has been poisoned. It has been turned into its ferric state, its +3 state, and it can't transport oxygen anymore. Okay? So methemoglobin is an abnormal form of hemoglobin that cannot transport oxygen. Does that make sense? Okay. And then finally, I want you guys to be familiar with these terms, these oxygen-related terms. What is FiO2? It's the fraction of inspired oxygen. Okay, that's the percentage of oxygen that you're breathing, right? What is S(a)O2? In pulmonary, a little a always means artery. That's a saturation of arterial oxygen. You guys okay with that? What is SpO2? What does the P stand for? No. P stands for pulse oximetry. Does that make sense? So SpO2 is not SaO2. Okay? So when you put a pulse oximeter on somebody, you cannot document that their SaO2 is 97%. Okay? SaO2 is measuring oxygen from an artery. Does that make sense? SpO2 is your pulse oximeter, right? Which is capillary. It's more capillary than arterial. So there can be a difference. That's why I want you guys to be sure that you do not equivocate those. Because I do see lots of charts where people write SaO2 96%. How the heck do you know that without an arterial blood gas? You don't. They're just confused. You guys okay with that? Now, whenever you see a big A in pulmonology, a little a is an artery, a big A is alveoli. So P big AO2 would be the pressure of oxygen in the alveoli. Does that make sense? Okay. And then what is HBG? What is that? Of what? Hemoglobin. And HCT is your hematocrit. Cool. All right. I think we've done enough damage for today. What do you guys think? On Monday, we'll go into carbon dioxide transport and all the acid-base goodness that we can muster. All right. Good deal. Thanks for hanging in.